Hi, my name is Bob Greenyett, and I'm a volunteer with the Martin Fleischmann Memorial Project. Now we're going to look at Griffin blocks, electrode here from Griffin Labs. And so we will open up the door to the SEM and throw that in there now. And here we go. So this is our target here. And what I noticed when I was looking at this is it seems to have a circle area here, and another one down here. So have we got a magnetohydrodynamic structure forming on this? We shall see, but it's quite exciting already. So I'll take a shot of that. And we will put it into the SEM. There are actually pits here, here, and here. Okay. Don't see a lot there. Of course, we might be quite close to it. No, there we go. We're starting to get something. There we go. A little bit out of focus. We'll try and adjust the contrast there. Okay, we're still in focus mode. Bit too much brightness there. Right, so I think we've got it in a bit low res here. So I'll have a high quality here. And I'll put it up a little bit higher so we can see what we're doing. Wow, it's definitely got some structures here, hasn't it? So I think what we'll do is we'll go to the boundary here and we'll find out what the actual base material is, bearing in mind that it's been stuck in the device for a period of time. So it's obviously got some blobs here of, one might expect, carbon. There we go. Okay. So we'll take an image of that. This is the ostensive raw material, other than these big blobs of something, which we could probably expect a carbon. Something heavy there. Okay, so if we just do some EDS here, and we'll take a quick look over here. Let's get the do a bit on this edge here where this light piece is. Okay, so first we'll have a look at that, and then we'll look at these spots, and then we'll look at this. What do we have? Go back and take an image here. I'm going to be taking 16-bit images, so there'll be plenty of data to play with. So, being supposedly a piece of aluminium, potentially this is straight aluminium. These might be bits of silicon. These, I think, are blobs of carbon, possibly from, if we're right in thinking that as EVO is involved, these would be depositions from that. And this might be some much heavier element. We'll find out in a minute. Okay, so first off, what is the bulk of the material? Well, it does look like it might be aluminium oxide, mostly aluminium, as we might expect. Does appear to be some carbon in there. If there's EVOs involved, that will be synthesized. But we're on the mostly cut area outside of the main affected area. Still, fair chunk of carbon in there. 5% atomic concentration. Okay, so I think that's good enough for that. We will have a look at what one of these lighter areas is composed of. Looks like this is part of the original material. See the chunk in there. And as we suspected, it's got the silicon in there. Silicon inclusions. Now, Georgi Messiat said that if you wanted to have a good ecton emitter, ectons are EVOs, you should look to have inclusions in there, potentially of silicon. Now this is interesting. What's this manganese business going on here? Is that really manganese? There's definitely a signal there, isn't there? Would appear. And iron. Okay. Could this be something to do with the cutting disc? Possibly. Often you find bits of iron in aluminium when it's been, recycled. It's not ultra pure. But that might actually be playing a positive role in terms of creating the etheric matter rays. But if I wanted very pure rays, I might want to try a more pure aluminium, possibly with some silicon inclusions. Right, so that is the mid element thing there. So that has some silicon and so forth, and iron and magnesium. We'll have a look at this bit, which looks like it's got fairly large. We'll do a region on it because it's going to have a bunch of elements in there. Well, tin. Now, I wonder if he is using a tin silver alloy to fuse the electrode on the back to solder it on there, possibly. Anyway, that's a lot of tin in there. Not getting a whole lot of counts here. Silly Bob. Bob hasn't got the SEM at a high energy level, so that might be confusing our signals here. So I'm going to stop that. I'm going to stop it, and we're going to probably do these things again with the right beam energy. Sorry guys, I have been away from it for a little bit. Let's try that again, shall we? I'll always get it right. Right, auto contrast. There we go. And we will go autofocus. We'll take an image, and we'll try taking our samples again. But I think probably it's going to be a similar story. You can imagine that these parts are much harder, so if it got caught, this might actually be from the cutting wheel, so these might even be little parts of the cutting disc or sandpaper. Probably one of the ways you can easily contaminate this. Right, I'm going to do a mix, and we will go and look at the elements again. So I'm going to delete these. And shall we have a look again? Here we go. We will look at our background material first. Story is pretty similar. We're getting plenty of counts. Now we have a green light down here. You want to see a green light down here? Okay, that's looking a little bit more sensible. Carbon, oxygen, and aluminium. Okay, we'll have a look at one of these inclusions, like that one. Okay. Doing weird stuff today. It's not allowing me to select that. Anyway, That's definitely determined that pretty well. Okay, it's not stopping, it's not responding. Oh, I got that in the wrong place, silly me. Stop. Not doing very well today. Let's try that again. Okay, so definitely it's got silicon, manganese and iron in these inclusions. Much better green. It's really seeing the elements there properly. By atomic concentration, it's still a lot of aluminium. That's pretty settled, and we will do a little area on this blob here, which we think is probably tin. And it could be the solder. Okay, it's too close working distance to do the EDS properly here. Struggling a bit. We might have to move it down in the device. It will take a few high-res images before we do that. Yeah, it's pretty low count. Anyway, a little bit of silver, a little bit of tin. Okay. So we might have to move this down a bit. Because that's about as far as we can get out from that, which is not very far. We'll have a look in the middle of this area here, this white area. Is this aluminium oxide? Interesting. You get very good imaging at this distance. So the full distance there is 30 microns at that point here. Let's see what we have. Move it over a little bit. Okay. It's like crystals here. Looks like a landscape, doesn't it? Many places where you have pinching of electrons. We will switch that to the different detectors here. So secondary electron detector gives you more of a view on the 3D nature of it. Now, when you get these pinching things going on, you often find on Hutchison samples, you get heavier elements on the pinch. So it'll be interesting to see if something similar is going on here. We'll select an area, something like down here, where we've got some background areas and then some pinched areas. And we will do one with BSD full. This should give us different elements. Yeah, so definitely different elements going on there. Then these images will line up. Is that a diamond? I don't know. We'll have a look at that area up there. In fact, there's several things that are crystal shape here, diamond shape maybe. We'll have a look. Okay, so we're going to go up here into this particular area here. Of course, if it's made diamonds, then they are the most efficient electron emitters. We found diamonds synthesized in 2013 on Francesco Celani's Constantan wire. It's definitely here looks like an electronic fluid, magnetic fluid type of arrangement going on here. We shall see. Let's go for SED full. Yeah, these areas are definitely flat. So I'm going to put that on a mix so we can see it with some depth and some element concentration variance, and then we will do some SEM. So this might be pure carbon in the form of a diamond. This might be a diamond covered with other sputtered material. Or there might be calcium, I don't know, let's see. Calcium is something that this system tends to produce, and we didn't see that on the boundary materials, did we? No calcium at all. Very interesting if there's some calcium here. Okay, so I'm going to put that to point. We'll change the way it is presenting this. And we will go into our thing and we will choose another area here. And we will see what the background section is, this kind of consistent area here. Hopefully we're not too close. So we've got a green thing here, but let's see. Well, it's aluminium and oxygen. Aluminium oxide, aluminum oxide with a little bit of carbon. Doesn't look much different from what we saw up here. 74,817, and that is 62,3. Actually, it's actually more aluminium here. So the white might be more aluminium oxide, maybe. Very clean. And we'll chuck a few spots in here. So I think we want to do this one. Interesting. Right, I think that's settled. Copper. Copper? It's got copper now. Interesting. So maybe the black bit is copper oxide. Where has the copper come from? It's not a lot by atomics, but it's definitely there. Could these be copper oxides? Well, iron, but it looks like we had iron inclusions on the boundary. Is that higher than it was on the boundary? 8.3 and 8.1. 8.7 and 9. 9. Is this carbon or is this more of the same? Well, that's odd. Oh, this is mostly carbon. So this might be diamond and this might be a diamond that's coated, as we said. Yeah, this is very clear crystal under here. So look at that. This one here, which is apparently coated, 17.6. What is the original boundary there? Okay, so it's still got 42% there, but this one is 80.6% carbon. Should probably go back to the boundary and have a look at those spots. We'll have a look at this line here as well. This might be something interesting. That is a lot by atoms. Of course, when you're seeing this aluminium, it might be just because the beam is picking up some aluminium from around it. This really might be more pure, or even under it. It might be pure carbon. It might be a very diamond. And we have some very white blobs here. Those are heavier elements. We'll have a look at those. Maybe they're copper. Maybe this is copper rich. We see copper in aluminium oxide in a Hutchison sample in the center of affected areas. So let's have a look at this ridge here. Well, look at that. Copper and nickel. So my hypothesis would be that these very pinched areas here might be blobs of copper, or possibly even the tin, but that is very interesting. Look at that. Very clear signals. Let's have a look at this. It's not quite so white there, but when it's finished, settle down there. Yeah, there's copper there. Not a lot. 1%. Yeah, there was 3.7% on this ridge. I wonder if the ridges are like that all over. Huh. We will turn this over and have a look at the back side to close out, to see the area that isn't really exposed so much to the particle and ion movement. Yeah, the copper tries to come in here, but it's saturated. It is there, but it's It's not a very strong signal in this part. It might just be that I'm missing it. Anyway, I think we'll have plenty of opportunity to look at other areas. Just going to have a look at this ridge here. It's one of these ridges. And we'll look at, maybe we'll look at this ridge here. There we go, the copper's coming back in there. So if we don't see any copper on the backside, this would appear to be making copper. Now, if this really is synthesizing elements, this shows that Nikola Tesla would have been synthesizing elements about 130 years ago in these type of tubes, which is really rather amazing.